I'm going to use the baby's crawl data in the open intro package. First, I run library open intro. And this is what the data looks like. I want to fit a model where we predict the average crawling age using the temperature. I'm going to use a new syntax for plotting. We've been using plot x comma y, but I'm going to switch to plot y squiggle x. It makes the same plot, but this syntax matches the syntax we use for linear regression, so I like to use this version. To fit a simple linear regression, it's lm y squiggle x. And I tend to store these things as lmod for linear model. It's useful for accessing the various elements. Note that I can avoid using the dollar signs by putting this data command in here. That tends to keep things cleaner and easier to read. The output gives the intercept and the slope. It's saying that when the temperature is 0, the average crawling age is predicted to be 35.68 weeks. For every 1 degree increase in temperature, the average crawling age is predicted to decrease by 0.07774 weeks. This command, AB line lmod, will add the fitted line to the plot. The correlation coefficient is negative 0.7, which is all right. You don't want to see it get too far below 0.7 or so. This isn't an especially strong linear relationship, but it's still good enough that we would try and fit a line to this. Here are the residuals. The residuals are the observed values minus the predicted values. If you look at this point here, the temperature is 48. This was in November. The observed crawling age was 33.4. The predicted crawling age is 35.68 plus negative 0.0774 times 48, 31.95. And the observed minus predicted was 1.45, and that's this one here. It's off a little due to rounding, but these residuals are the observed crawling ages minus the ages predicted by the line for those observed temperatures. To check the fit, we examine residual plots. These are residuals on the y-axis, fitted values on the x-axis. You can also use explanatory variables on the x-axis. Let me try that. Doesn't make much difference. You'll see the book do this, but fitted makes more sense when we get to multiple linear regression. So I like to stick with residuals versus fitted. We want to see these things evenly spread out about zero. With no pattern, they look pretty good except for this one outlier down here, and I'll look at how to deal with this in a minute, but overall I think this looks pretty good. To check the normality assumption, we can draw a histogram of the residuals. This looks all right. It looks a little skewed, but remember, this is just one observation. Apart from that, it looks good, and that's the outlier. We can also make a QQ plot. The command is QQ norm, and then QQ line puts in the line. And what it's doing is comparing the quantiles of the residuals to the quantiles of a normal distribution. Remember that quantile is like a percentile. We want it to fit the line well. There's usually some disagreement at the very ends, but you don't want it to go too far off too often. I'd say this looks all right. Let me take a sample of 12 normal random variables and see how that compares to our residuals. I'll run this a few times. Now you see, some of these look even worse, and this is from data that we know is normal. So you can't put too much faith in these things at small sample sizes. Let me make a bigger sample size. Now you see it's better. It still tends to disagree at the very tails, but this is what a good QQ plot looks like. So ours wasn't too bad at all. If we know what order our data was collected in, we can look at the residuals in order of collection to see if there's some kind of pattern that would indicate serial correlation. That would be a violation of our independence assumption. The book gets into this in section 9.3, which I haven't assigned, but you can read more about it there. I'm going to plot the residuals by birth month. I get this weird kind of line plot. That's because the variable on the x-axis is categorical. It's the months. I can put it in this as numeric argument, and then R will treat them as numbers, and I get the points. Now you can see it goes down, up, down, down, up, down, up, down, up, down, up. The only time the pattern gets broken is here. So that's a reason to be concerned that we have serial correlation in this case, but it's a small sample and the pattern does get broken, so I'm going to ignore this. I think it'll be okay. The summary command will give us more information. These are the estimates of the intercept and slope. Then we have the standard errors, t-statistics, and this last column is the p-values. The null hypothesis is that the slope parameter is 0. The p-value is 0.0113, which means at the 0.05 level, we reject the null hypothesis and conclude that the slope parameter is different from 0. we conclude that the temperature is a significant predictor of the average crawling age. Our R squared is 0.4896, which isn't great, but it's what I expected given the correlation coefficient. The correlation coefficient squared is R squared for simple linear regression. To deal with outliers, you first want to check to see if they affect the fit. The outlier was in May, which was the 5th observation. I'm going to make a new data set without the outlier. Now I fit the same model. The residual plots look fine. If we look at the summary output, the intercept has gone from 35.68 to 35.84, and the slope went from negative 0.07774 to negative 0.07562. R squared has gone up quite a bit, but I think that because the coefficients don't seem that different, I'd prefer to just stick with the original model and leave the outlier in there. If I decided to take it out, I would publish both results and let the audience decide what to make of the outlier, because I don't have any good reason to remove it.